Hey guys, we're going to keep going with our mechanics. The next little section that we're going to be looking at is work and energy. Now we had a look at the concept of work and what it is and how the basics of it works. The next step is to go to Emech, mechanical energy. And this will also involve some understanding of closed systems, where there's no friction, no applied force, everything's nice and simple. So let's go through this a little bit. So first of all, what is mechanical energy? The mechanical energy of an object is the sum of the kinetic energy and the gravitational potential energy of that object. Summarized beautifully by that little equation, which actually isn't on your formula sheet, so you've got to remember that one. Emech equals EK plus EP. Alrighty. Okay, so let's get our heads around what mechanical energy is and how it fits in to the bigger picture of energy. You may remember from back, and I think it was in grade 9, that you guys learned the conservation of energy. Energy can't be created or destroyed, but it can be transferred from one form to another. So for example, we can have electrical energy coming into a light bulb. Some of that goes to heat, some of it goes to light. They're all different forms of energy that will stay within the whole system. They can be transferred from one form to another, but not destroyed. Now, within our overall energy system, we can set aside two special forms of energy, the ones that we were talking about earlier, EK and EP. And they can go in a very exclusive little VIP zone of their own. Because mechanical energy in itself can actually be conserved as well. So kinetic energy can get turned into potential energy, and then the potential energy turned back into kinetic energy. Okay, so let's get our heads around how this actually works. Now, just a bit of an analogy. What this could be like is a water reservoir, or like a JoJo tank or something, filled up with water. Now, as long as the water doesn't escape, so if it's a sealed, closed system, the water can wobble around as much as it wants, it can even evaporate and condense back in again. As long as there's no leaks or anything, the water will stay in there. So, as an example, imagine this ruler, okay? I'm going to do a little bit of a scenario with this ruler as a closed system. This is quite a common example of a closed system, of a pendulum. It's swinging backwards and forwards, going from one form of energy to the other, potential to kinetic, kinetic to potential, back again. Now this, in theory, if there's no external forces, could just go on and on and on and on forever and ever. But obviously it's not a perfect system, and in fact I'm driving it by wobbling it backwards and forwards. If I just let it be, very quickly it's going to run out of energy. So what's happened, thank you very much, is that the water is kind of leaking out of the reservoir, and our energy is being decreased by negative work. If I wanted to top up my reservoir again, I could put a hose pipe into it, for example, or the rainwater from the gutter, and it'll top it back up. But both of those have broken our system. So this is no longer a closed system, it's an open system. So what we want to deal with now is the simple version where there are no external forces. There's no leaks, there's no hose pipes, it's just the water within the system. And it can go from one to the other, from EP to EK or EK to EP, but it doesn't escape. So a closed system, no external forces, no friction, no applied force. I hope that makes sense. Let's move on. Okay, now there's our formula that kind of summarizes what the conservation of mechanical energy is all about. The initial mechanical energy is equal to the final mechanical energy. In other words, nothing's changed. Whatever we had at the beginning, we have at the end. Okay, so the total mechanical energy in a closed system remains constant. That's a nice way to say it. The total mechanical energy in a closed system remains constant. So now we get into our problem, and what we have to do is break that down. So the EK plus EP at the beginning, initial and initial, is equal to the EK and the EP at the end, final, final. Okay? So if you happen to know it at that high level, you can put in your values. Most often though, we actually go one step deeper, where we break it down into EK being half mv squared, as you know, and EP being mgh. So you have to look at the scenario before and the scenario after. And most often you'll be given enough information to sub in all sorts of values. You'll pick up loads of marks through your substitutions, of course, and there'll be one thing that you have to find. For example, the final velocity or the height to which something goes. Okay, So let's have a quick look at the three different scenarios you'll come across. The first one would be a pendulum, like I showed you with that ruler. All right, it can swing backwards and forwards like that. Now, obviously, when it's at the top, the type of energy it has is EP. If it's at rest, its EK is in fact at 0. Then it swings down to the bottom. It gets going faster and faster, so it actually has EK. EK goes to be a maximum, and EP now goes to 0 because it's at 0 height. And then once it goes back up the other side, when it gets to the top, EP once again is back to a maximum, and as it stops and turns around, EK is at 0. So this, as I said, could go on and on and on ad infinitum until you add friction or an applied force. So that's one scenario you quite regularly come across. It could be Spider-Man swinging down from a building. It could be an orangutan from a tree, perhaps. Okay, a more simple example, which does actually come up from time to time, where you have to use energy principles. If they force you to do it, you must use these equations we've just been talking about. Of course, if it's just a simple free-falling object, you could use equations of motion. But if the question says using energy principles, you must use this method. So you would then say, well, it's got EP at the top and it's got no EK. But at the bottom, it has EK, which is now at our maximum, and EP is gone to 0. So that's a simple application. It could be a person jumping on a trampoline or any kind of up and down motion. The third example, which is quite common as well, would be a roller coaster or a marble on a track. It can't be a car because a car has an engine, which would be an applied force. So it has to be something freewheeling, even a bicycle, freewheeling, a skateboard, anything that doesn't have a motor. So let's draw ourselves a little roller coaster at the top of the hill here. That might have an initial velocity, so you've got to include the initial EK. And of course, being at the top of the hill, it's got some height, therefore some potential energy. And the question will say, well, maybe how fast did it go when it was reaching at the bottom? Well, sorry, how fast did it go when it was at the bottom? What is the final velocity? It might ask you to find out how high the next hill is if you knew how fast it was going. So there's all sorts of different questions you could have with something like this. Okay, so as promised, let's have a quick look at an example. Now, earlier I mentioned an orangutan, so here we go. This is a question that similar to the kind of question you might get in an exam paper. A 45 kg orangutan swings down from a tree on a rope to pick up a pineapple off the ground. If the orangutan was 5 meters off the ground, there's a helpful piece of information, what is the final speed of the orangutan when it picked up the pineapple? Okay, so we're told how high it was off the ground, that's its initial height, and what is the final speed? That'll be VF. Right, so let's go through to how we're going to tackle this one. Let's get our information together using our little RefWa table. So it's a 45 kg orangutan. Initial velocity was what, do you think? He's hanging up there in the tree. Was he going anywhere? No, he wasn't going anywhere. He was going at 0 meters per second. Initial height, we're told, was 5 meters. The final height, well, when Ollie, the orangutan, got down to the bottom, he didn't have any height. He was cruising across the grass. Okay, the acceleration, interesting one. I know you're tempted to put in 9.8, but you've got to think, well, is he free falling? Remember what free fall is, just a quick recap here. Free fall is when the only force acting on an object is gravity. Is that the only force acting on Ollie? Well, he's certainly got gravity acting on him, but what else has he got acting on him? He's hanging onto the rope, otherwise he's just going to fall straight out the tree. So the tension of the rope means that he's not free falling. You can't say that there's 9.8. Helpful little pointer there. And we're being asked to find the final velocity. So quickly, let's whip through how this would go. We're going to use, because there's no friction involved, because there's no applied forces involved, you identify, yes, this is a closed system. I can use my conservation of Emech rule. Conservation of Emech. Okay, so we start with that first equation. Emech initial is equal to Emech final. We break it down. Half mv squared I, half mv I squared plus mghi is half mvf squared plus mghf. All right. So you can see how I've separated the before and the after. Now let's plug in some of our values, which I'm just pulling from my table on the left-hand side. Well, vi we know is 0, therefore that whole term we can consider to be 0 at the beginning. The second one, m is 45, 9.8 is g, h is 5 meters above the ground initially. Now on the other side, half m, so half times 45, and the final velocity that we're trying to find. So that's going to be our final answer. And of course, the height at the end when he comes down to the ground is actually 0, so that, again, the last term in our working is 0. Rearranging things, we get the fact that the VF squared on the right, put everything else on the left. You can see quite nicely that the 45 cancels with the 45. You could have in fact even done it earlier if you wanted to, but it's nicer to see it in the equation. Then we solve for that. We get 98 on the left is VF squared. Therefore, our final velocity is 9.9 meters per second. So that gives an idea of how this example could work. Now it's your turn to do a bit of practice. Good luck. Hope you have fun. Cheers, cheers. Bye.